Hello everyone. So in this one shot, I'm going to cover electromagnetic waves. So I'll cover all concepts and the problems that can be asked in your board exams. So let us see the syllabus first. So first we'll see the concept of displacement current. Then we'll talk about what are electromagnetic waves, how we can generate them, and what are their characteristics, and what is the transverse nature of electromagnetic radiation. Then the electromagnetic spectrum, which is divided into multiple waves, right? Like radio waves, microwaves, infrared, visible spectrum, ultraviolet, X-rays, and gamma rays. So we'll talk about these electromagnetic radiations, how we can generate them, and what are their uses. Now let us see the concept of displacement current. It was proposed by Maxwell, and it is given as epsilon naught d phi E by dt, where epsilon naught is the permittivity of free space and d phi E by dt is the rate of change of electric flux. So he come across this the concept of displacement current when he was studying charging of capacitor. So if I show you the experimental setup, this is a parallel plate capacitor, and this plate is at a high potential and this plate is at low potential. So he applied Ampere's circular law on this particular Amperian loop. Now he considered an Amperian loop between the plates of the capacitor, where the plane of this loop is parallel to the plates. And if we apply Ampere's circular law, integral B dot dl, the right hand side, which is mu naught times the current which is piercing the loop. In this case, there is no current which is piercing. So the right hand side comes out to be 0. So from here, B comes out to be 0. But if we place a compass needle between the plates, it shows deflection. So it means something is missing in Ampere's law. So he introduced this term to the right hand side and he modified Ampere's law. And now this equation, which is mu naught times I conduction plus I displacement. Now this equation is applicable for any scenario. Now if we talk about the electromagnetic radiation for EM waves, so EM waves are propagating in vacuum. So there is no conduction current. So we can see in case of EM wave, IC will be 0. So Ampere's law will be integral B dot dl times mu naught times epsilon naught d phi E by dt. So in case of conduction current, if there is no electric field, there is no rate of change of electric flux. In that case, the displacement current will be 0. So we have to remember this. And now let us see some of the questions which were asked from the displacement current. So let us see the first question. The charging current for a capacitor is 0.25 ampere. What is the displacement current across its plate? Let us see. So we have given charging current which is IC, which is 0.25 ampere. If the capacitor is getting charged, so let me just show you. If I consider an Amperian loop here, so the displacement current will be given as epsilon naught d phi E by dt. And let us say the charge on the capacitor is Q. So we can say the electric flux will be electric field times the area of cross section, right? Area of the plates. And in this case, now this is basically the electric field lines, right? So I can write E as sigma upon epsilon naught. So this is the field in between the plates of the capacitor, and that we have studied in capacitors, times A. So if Q is the charge, so Q upon A epsilon naught times A. So A will get cancelled out. So if you want to find d phi E by dt, so d phi E by dt will be 1 by epsilon naught times dq by dt. And we know that epsilon naught d phi E by dt comes out to be dq by dt. So where dq by dt is nothing but the conduction current and the left hand side is nothing but the displacement current. So we can say their values will be same. So it will be 0.25 ampere. Right, now let us see the next question. A capacitor has been charged by a DC source. What are the magnitude of the conduction and the displacement current when it is fully charged? So when it is fully charged, we know that when the capacitor is fully charged, it behaves like an open circuit. There will be no conduction current. If there is no conduction current, we can say the displacement current will also be 0, because the electric field has stabilized and the flux of electric field which is piercing through that Amperian loop will be 0. If flux is not changing, that will be non-zero but a constant value. If the flux is not changing, then d phi E by dt will be 0. So d phi E by dt is 0 if electric field is constant, right? So if the rate of change of electric flux is 0, we can say displacement current will be 0, which is given by epsilon naught times d phi E by dt. Right, so now let us see the next question. A capacitor made of two parallel plates, each of plate area A and separation D, is being charged by an electric external AC source. Show that the displacement current inside the capacitor is the same as the current charging the capacitor, and that we have already discussed. If I show the electric field will be Q upon A epsilon naught. That is the electric field. Now what is the flux of electric field? That will be E times A. So that will be Q upon A epsilon naught times A. So this is Q by epsilon naught. So if you differentiate this d phi E by dt, it comes out to be dq by dt times 1 by epsilon naught. And from here epsilon naught d phi E by dt comes out to be dq by dt. Now the right hand side is the conduction current and the left hand side is the displacement current. So we can say their values will be same. So that we have to prove in this particular question. I hope whatever illustration that we have covered for displacement current are clear to you. Now let us see the next concept where these are the four equations, or we'll call them Maxwell's equation, and based on these four equations we can define any phenomena in electromagnetism. Now the first equation is Gauss law for electricity, and that we have studied in electrostatics. Integral E dot ds is Q enclosed by epsilon naught. Second is Gauss law for magnetism, and where we have the magnetic flux through any closed surface is 0. Third is Faraday's law that we have discussed in electromagnetic induction, that is integral E dot dl is equals to negative of rate of change of magnetic flux. Then Ampere's Maxwell law that we have just discussed, integral B dot dl is mu naught I plus mu naught epsilon naught d phi E by dt. So do remember these four equations that can be asked in your exam. Now let us see how electromagnetic radiations are being produced. So let us see. So first of all, to produce electromagnetic radiation, we require an oscillating charged particle. So an oscillating and accelerated charged particle is the source of electromagnetic wave. And how it can produce? An oscillating charge produces oscillating electric field in space. Now this oscillating electric field by Faraday's law, this oscillating electric field by Ampere's Maxwell law produces oscillating magnetic field, right? And when we have oscillating magnetic field which is changing with time, it will induce electric field, right? Then it becomes the source of electric field. So this phenomenon keeps on happening. So oscillating electric field will produce magnetic field, then the oscillating magnetic field will produce electric field, and it keeps on happening, and the electromagnetic radiation propagates in space. Now these oscillating electric field and magnetic field hence keep on regenerating each other, and the electromagnetic wave is produced. So you should remember how electromagnetic waves are produced. Now let us see the equation of electromagnetic wave. So I have shown an animation where we can see the electric field is oscillating in the y direction and the magnetic field is oscillating in the z direction, and the electromagnetic wave is propagating in the x direction. So let me show you the direction of propagation. So in this particular case, I cap is the direction of propagation of EM wave, and in J cap direction I can say it is the direction of electric field oscillation, and in K cap direction we have direction of magnetic field oscillation. And you should also remember that electric field, so we can say E cap cross B cap will give us the direction of propagation. So I'm saying I'm just representing it with N cap. So N cap is the direction of propagation. So we can remember this. Now if I want to show electromagnetic radiation, So we can show electromagnetic radiation either in terms of the oscillating electric field or in terms of the oscillating magnetic field. So we can say E vector will be E naught sine omega t minus x by v. And what is the direction of electric field? I can say it is in the j cap direction, right? So this is the equation of electromagnetic radiation in terms of electric field. Similarly, we can show magnetic field. So magnetic field will be B naught sine omega t minus x by v, and instead of j cap we'll write k cap. I hope it is clear. And you should also remember that the speed of, okay, right, so let me write v in terms of c, right, which is the speed of electromagnetic radiation in vacuum. So speed of EM wave is 3 into 10 raised per 8 meters per second in vacuum. And this C can be given by E naught by B naught. So this formula you should remember. And C is also given by 1 upon root mu naught epsilon naught. We'll also study this in the future part of the video. So I hope these concepts are clear. What are the equation of electromagnetic radiation? So do remember this. Now let us see the properties of electromagnetic radiation. So these waves do not carry any charge, right? And these waves are not deflected by electric field and magnetic field. And they travel with the speed of light, that is 3 into 10 raised per 8 meters per second in vacuum. And the frequency of electromagnetic wave does not change when it goes from one medium to another, only the wavelength changes. And these waves are transverse in nature, hence they can be polarized. So we have seen they have oscillating electric field and magnetic field. And one more thing I forgot to mention, electric field and magnetic field are in phase. E and B are in phase. What does it mean? That both of these becomes minimum and maximum at the same time. And as you can see from the diagram, right, both are becoming maximum and minimum at the same time. Okay, right. So now let us see the relation between the speed, refractive index, permittivity, and permeability. So as I mentioned, speed of light in vacuum is given by 1 upon square root of mu naught times epsilon naught. Now if I want to show the speed in a particular medium, so in that case we'll use the permeability and the permittivity of that medium. So the formula will become 1 upon square root of mu times epsilon. So and we know that what is mu? Mu is mu naught times mu relative. And what is epsilon? Epsilon is epsilon naught times epsilon relative. So this can be written as, so we can be written as 1 upon square root of mu naught mu r epsilon r, and 1 upon square root of mu naught epsilon naught is nothing but the speed of light in vacuum. So we can say V is equals to C upon square root of mu r epsilon r. Now we have very important formula. So we know the refractive index. If I take n as the refractive index of the medium, and that you must have studied in the optics in class 10th, and it is given as speed of light in vacuum to the speed of light in that particular medium. So it comes out to be square root of mu r epsilon r. So do remember this formula for refractive index of a particular medium. Now let us see some question. An EM wave is traveling in a medium with a velocity v I cap. Draw a sketch showing the propagation of EM wave, indicating the direction of the oscillating electric field and the magnetic field. That we have already seen in the animation. So if I show three mutually perpendicular direction. Now this is the x direction, this is y direction, this is positive z direction. So x is the direction of propagation that is given, and it is propagating with the speed v in that direction. So in y-x plane we can show oscillating electric field, right? Like this. So this is the oscillating electric field, like this we can show. And in the xz plane we have oscillating magnetic field. and both electric field and magnetic field are in phase. So they'll become maximum and minimum at the same time. So I can show it like this. I hope it is clear. So the blue one is the magnetic field and the red one is the electric field. So like this, we can show the electromagnetic radiation which is propagating in the x direction. So this is the direction of propagation. Okay, now let us see the next part. How are the magnitude of electric field and magnetic field related to the velocity of the EM wave? So E naught by B naught is the speed of the electromagnetic wave. So do remember this formula as well. Now let's see another question. So we have given an oscillating magnetic field in a plane electromagnetic wave is given by 8 into 10 raised to minus 6 sine 2 into 10 raised to 11 t plus 300 pi x, and it is in Tesla. Calculate the wavelength of the electromagnetic wave. So if I write down in general form, so we have B naught sine, this will be omega t plus kx, right? Omega t plus kx, where omega is the angular frequency and k is the angular wave number. So if I compare these two equations, so omega is 2 into 10 raised to 11 and k is 300 pi, right? So we have to find the wavelength. So to find and the angular wave number is given by 2 pi by lambda. So 300 pi, so it will give us 150. So lambda will be 1 upon 150. So if I multiply this with 100, so we'll get lambda in centimeters. So that will be 2 by 3 centimeters. Write down the expression for oscillating electric field. So now this is the expression for magnetic field. So for electric field, we can write it as, so what is the speed? Let us first find out the speed. So speed will be given by omega by k, and omega is 2 into 10 raised to 11 divided by k is 300 pi, right? So from here we can say it will be 2 into 10 raised to 9 divided by 3 pi. Now that is the speed, and E naught by B naught is given as speed, right? So from here we can find E naught. So E naught will be C times B naught, and B naught is given as 8 into 10 raised to minus 6. So 8 into 10 raised to minus 6 multiplied with the speed of the electromagnetic radiation, that is 2 by 3 pi into 10 raised to 9. So from here we have 16 upon 3 pi times 10 raised to 3. So we can say electric field will be given by 16 upon 3 pi times 10 raised to 3 sine 2 into 10 raised to 11 t plus 300 pi x. So remaining the sign terms will remain same, only the amplitude of the electric field will change. And since the direction of magnetic field is not given, so we cannot tell the direction of electric field. But if the magnetic field, say if I show you the direction, so I'm showing 3 mutually perpendicular direction. So the positive sign tells us that the electromagnetic radiation is propagating in the negative x direction. If there is a negative sign, it means it is propagating in the positive x direction. I forgot to mention that, but do remember, if there is a positive sign, means it is propagating in the negative x direction. If it is negative sign, then it is propagating in the positive x direction. Why x direction? Because here we have x. Okay, so it means the electromagnetic radiation is propagating if this direction is x and this is y and this is z, and it is propagating in this direction. If electric field is in this direction, in the z direction, right? If electric field is in the z direction, then magnetic field has to be in the y direction, because E cross B will give us the direction of the propagation, E cross B. Right, so we can say electric field will be in the positive z direction. So I can show it in vector form, and we can add a k cap vector with the magnitude. So I hope this question is clear to you. Right, so now let us see the concept of energy density and the intensity of electromagnetic radiation. So energy density is given by average energy density, right? Will be given by half epsilon naught E naught square, or it is also equals to 1 by 2 mu naught B naught square. I haven't seen any question based on this concept, but do remember the formula, right? And the energy is equally, you can say equally contained in electric field and magnetic field. So we can say the energy density is corresponding to electric field and magnetic field will be in 1:1. So do remember that. And what is the intensity? So intensity will be given by 1 by 2 epsilon naught E naught square times C, where C is the speed of the electromagnetic wave, and it can also be given by 1 by 2 mu naught B naught square times C. So if you want to show the energy density and intensity in terms of the RMS value of electric field and magnetic field, and we know that E RMS is equals to E naught by root 2. Similarly, B RMS will be B naught by root 2. So we can replace E RMS and B RMS, we can replace E naught and B naught in terms of E RMS and B RMS in these equations, and we can derive the formula for that. Right, so now let us see the last topic. It is the electromagnetic spectrum. So if we show electromagnetic radiation, so we have a wide spectrum. On the extreme left, so if you're going in the right direction, the wavelength is increasing, right? So in this direction, the wavelength is increasing, lambda increases. And if you're going in the left direction, the wavelength decreases, or we can say in this direction, the frequency increases. Frequency increases in the left direction. Greater the frequency, more the energy of the photons of that electromagnetic radiation. And greater the frequency, you can say more is the penetrating power, or you can say the smaller the wavelength, more is the penetrating power. So which one are more harmful? Which are on the left side of the spectrum, which are having high frequency. So do remember this. So then first we have gamma, then we have X-rays in the order of increasing wavelength, then ultraviolet, then the visible spectrum, then infrared, then microwave, then radio wave. So do remember these different types of radiation. Now we're going to study these different radiation one by one. So let's start with the radio wave. So radio waves, these are produced by the accelerated motion of charges in a conducting wire. So if there are charges which are oscillating, or if there are some AC current, you can say we can produce radio waves. And how they are being used? They are used in radio and television communication. And what are the frequency range? It will be 500 kilohertz to 1000 megahertz. Can you see the range is quite large? So due to that, we have to further divide this range into multiple waves. So first we have AM band, right? Amplitude modulated band, and it lies between 530 kilo to 1710 kilohertz. Do remember this, right? Because I have seen questions where they have asked about the range of the frequency range. And then we have higher frequency up to 54 hertz. These are known as short wave bands. Then for TV communication, so suppose if you have to if we require some signal to get to our TV, so we require 54 megahertz to 890 megahertz of frequency range. And then the FM radios that we listen on our radios, right? So these FM stands for frequency modulated, right? Frequency modulated. And the frequency FM radio band is 88 megahertz to 108 megahertz. You must have heard of 93.5 megahertz, 91 megahertz, right? So these are basically the frequencies on which those radio stations are being operated. Then the voice communication, like if I call you, right, and then we'll talk, right? So the voice signals, those are being sent at ultra high frequency, which is known as UHF. So do remember how these are being produced and what are the frequency ranges and what are the uses. Now the next type of electromagnetic radiation is microwave, and it has a frequency of the order of gigahertz, right? And it is being produced by special vacuum tubes known as klystrons and magnetrons, right? And it is being used in the radar system where we can detect the aircrafts in the sky, and also for the aircraft navigation. And it is also being used by the police officer, the traffic police officer, which can detect the speed of fast moving car. So it is used in speed guns, where we can also use speed guns to check the speed of the tennis serve or the ball by a baller, right? And also the speed of the automobiles. And there is one more important use that we use on a daily basis is the microwave ovens. So in microwave, we use microwaves, right? In such oven, the frequency of microwave is selected to match the resonant frequency of the water molecules. And if it matches with the water molecule, then the water molecule acquire tremendous amount of kinetic energy. And due to this kinetic energy, it will heat up the food which is placed in the microwave oven. And this raises the temperature and any food containing water. So the prerequisite to use microwave is the food should contain some water. Right, now let us see how infrared waves are being produced and what are the application of infrared waves. So these are produced by hot bodies and molecules, and these are sometimes referred as heat waves because water molecule present in most material readily absorbs these radiation, and due to which the temperature of those bodies will increase. It lies in the lower frequency end of the visible spectrum. And now let us see some of the application of infrared radiation. So first is the infrared lamps, and these lamps are being used in physical therapy. And the second and very most crucial application of these radiation is the earth is able to maintain its warmth through greenhouse effect. Now let us see how this is happening. So when the light rays coming from the sun, so incoming visible light is absorbed by the earth's surface, and then the earth re-radiate as infrared. So the rays he is absorbing as visible light, and it is re-radiating it in infrared spectrum. And these infrared are being trapped by the water molecule and the carbon dioxide present in the atmosphere. And due to this, the earth is able to maintain its warmth. The another important application is infrared detectors, which are being used in earth satellites, and these satellites are being used for military purposes and to observe growth of crops. And there is another important application which we use in day-to-day basis is the LEDs, which are being used in the remotes, switches of TV sets and the video recorders. So these do remember how they are being generated, what are the important applications of infrared radiation. And one more thing I would like to mention here, if Earth doesn't have any atmosphere, then what would happen? The Earth is not able to trap infrared radiation and the temperature of the Earth will decrease. So now let us see what are visible rays or that spectrum, visible spectrum. So these are the only electromagnetic rays which can be detected by human eye. And what is the frequency range? It will be 4 into 10 raised to 14 hertz to 7 into 10 raised to 14 hertz, or in nanometer we can show it as in wavelength range will be 400 to 700 nanometer. So human eyes are sensitive to this range of wavelength, right? But that is not true for all species. So snake can detect infrared waves, whereas there are certain insect which can see up to a ultraviolet radiation, right? So do remember these important facts. Now let us see what are ultraviolet waves, how are these being generated and how we can use them. So the frequency is, so the wavelength range is 400 nanometer to 0.6 nanometer. So 0.6 to 400 nanometer. So that is the range. And these are produced by special lamps and very hot bodies. And sun is a source of ultraviolet rays. So we are receiving ultraviolet rays from the sun. But the ozone layer in the atmosphere, which is at the altitude of 40 to 50 kilometers, it absorbs UV radiations, and these UV radiations, if consumed in large amount, are harmful. So exposure to UV radiation cause tanning of the skin, and these UV radiations are absorbed by the ordinary glass. So if you are under a glass window, then there will be no effect of the UV radiation. So one can't get tanned or sunburned through glass windows. Is it clear? So welders, and if you talk about the welding, right? So the welders use some special goggles to prevent their eyes from the harmful UV rays which is being produced by the welding arcs. And we have already understand if a body is very hot and welding arc temperature is very is quite large, so due to which it will be able to produce ultraviolet radiation, and so that's why they have to wear special goggles. Right, so and very important application of ultraviolet radiation is, since their wavelength is less, they can be concentrated in a small region, and it is being used in eye surgery where high precision is required. So LASIK surgery, eye surgery, we use ultraviolet rays. And we can also use UV lamps to kill germs in water purifier. You must have seen some advertisement where they claim that we are using UV filters to kill germs. Right. So do remember these important facts about ultraviolet rays. Now let us see what are X-rays. And it is, again, it is very common. So whenever we have a fracture, we take the X-ray of that particular fracture part and we can see the fractured bone. So the range for X-ray is 10 raised to minus 4 nanometer to 10 nanometer. And it is being produced if we bombard high speed electron on a metal target, and it is being used as a diagnostic tool in medicine and as a treatment for certain form of cancer. And we can see fractured bones, and with the help of x-rays we can damage or destroy living tissues and organisms. So it is recommended to avoid exposure to x-rays because these are harmful, and always undergo x-ray scan if it is required. Right. So the last type of X-ray, last type of electromagnetic radiation is gamma rays, and these are the most penetrating radiation and most harmful. So the wavelength range is 10 raised to minus 14 meters to 10 raised to minus 10, and these are being produced in the nuclear reaction or the radioactive decay. And they can destroy cancer cells, so they are being used to destroy those cancer cells. But again, the exposure to these radiation should be avoided because these are extremely harmful for living tissues. Now let us see the illustration. So what is the frequency of electromagnetic waves produced by the oscillating charge of frequency nu? So an charged particle which is oscillating with frequency nu will produce electromagnetic radiation of the same frequency. So nu is the answer of this question. Right. So what type of questions comes from electromagnetic spectrum? All will be factual questions. Right. So whatever we have discussed. So do go through each and every electromagnetic radiation and do remember the entire electromagnetic spectrum. Right. So I hope whatever I have covered in this video is clear to you. So see you in the next video where I will cover ray optics. Thank you.